maybe so this is the notes that I've given you. First, you need to watch the video. And initially, I was intending to make my own videos, but when I review these YouTube videos, I found that they are very, very nice because they have animation and so on, which explain the principles that we need to see in terms of hydrostatic and flotation. So that's why I do not make my own videos, so I just refer to that. So if you watch those videos, I think it's very strong to explain the principles. Yeah? But in terms of the calculation, it's not in there. So you have to go through the notes. So the notes are only 8 pages, but and written in self-explanatory. So if you read, you should be able to understand it and follow the example. And then the exercises basically follow the example. If you can understand the example, you should be able to do the exercises. And finally, I ask you to do this quiz. So this quiz should be done only after you have completed everything. You have done number 1, number 2, you have done all the exercises, all the example exercises, then only you go to the quiz. Because I saw some of you did not do that. I think you have not done the exercise. That's why your answers to the quiz is very far away from the correct answers. Yeah. So it's okay. That quiz, I think, I've not given any points, any marks. It's just for you to check your understanding. So maybe we can do that later. That's no problem. So if you see in these notes, what we do is, as I said, first understand the concept. So the concept is given in the video. What should you do before reading these notes? So this is concept of Archimedes. And then reduction of weight of floating objects. When something is immersed in fluid, there is a buoyancy force pushing it up. Okay, so this is basically the explanation. And then, so this is the equation that we mainly use. Buoyancy force is equal to the weight of the displaced fluid. So that's the force. So I think it's very important point here. Note here, although buoyancy weight are strictly forces in Newton, because his weight will be m times g, which is this one. This is m times g here. Sorry. And so this is the displacement times g as well. So both are in forces here, forces. But the g cancel out. So finally, it's this m, which is the weight of the object, equals to the equal to the volume, the mass displacement. So this is mass in kilogram or in ton. This is mass in kilogram or in ton. But you see in most books, we just say buoyancy and weight. Still we say buoyancy and weight, but they are given in terms of units of tons and kilogram. So that's what we do here. So you need to understand that. So that's why you say sometimes you say mass displacement, sometimes you say weight displacement, but all the units are in kilogram. And same thing like buoyancy, you saw buoyancy. Buoyancy strictly it should be in Newton, but we say that is in kilogram or tons or pounds, which is a measure of mass. Yeah, because of the g being cancelled out from all the equations. Okay, so our first example is basically an immersed object. When something is immersed in the fluid, then the buoyancy should be able to push the support the object. Okay, and there is a reduction of weight. So the apparent weight is the weight of the object minus buoyancy. And as I said just now, we have g here, g here, g here. So all the g's cancel out. So that's why we say this is in ton, this is in ton, this is in ton, or kilogram, kilogram, kilogram. Yeah, so that's why weight and mass are used interchangeably. So this is the exercise. Later we look at the solution. So that's the exercise is exactly, well, almost exactly similar to the example. So this is example 1, 2.1. And the exercise is just to change the density. Do similar calculation, but change the density and put inside this table. What is the apparent weight when it's in oil, in muddy water, in mercury? We have done calculation for fresh water just now using 1 ton per meter cube, yeah, as the density. Then if you change the density, same thing inside oil, what's the apparent weight? Same thing inside muddy water, what's apparent weight? Same thing in mercury, what's apparent weight? So what can we conclude on relationship buoyancy and the density? So that one you can answer after you have done the calculation. And then the second part here is what makes the ship float. So we want to, of course, that's why there is that YouTube video about why ship float, yeah? So you can read this. And finally, we say the importance of density, yeah, because the thing is similar. So it's basically this formula is very, very important. Tiada maaf bagimu. There's no excuse for you not to remember this, that buoyancy of a floating object, yeah, is the same as the weight of the displaced fluid is equal to the sorry, when this one, yeah, buoyancy of the object is equal to the weight of the displaced fluid is equal to the weight of the object itself, the floating object. So if a ship weighs 2,000 tons, then the displaced water is also the weight of the displaced water is also 2,000 tons, and that's the buoyancy force. That's the buoyancy, which is 2,000 tons. Okay, so of course the unit is all in tons or kilogram. So that's the idea here. And here what we're going to see is just the effect of changing of buoyancy of density, because the displaced weight of water is equal to the volume of water times density. So as you change the density from lower to higher, then there'll be changes of the volume, the weight displacement. So, and then this example of the box. So normally we look at the length, breadth, and depth, and draft. So we consider two cases. If that box we know is draft, then automatically we can know the weight, because we can calculate the displaced volume, and we multiply the displaced volume with density, and we can get the draft. Yeah, so which is this one. So we can estimate the draft, or we can calculate exact draft if we know its weight, because we know the volume that need to be pushed aside. Okay, so exercise 2.2 is to do exactly the same question. Yeah. Okay, I think I made a mistake here. Here should be okay. So this is the there is a raw water here. Yeah, there's a raw water here. Okay, so just follow the example solution in the example and do the same calculation in exercise 2.2. Again, same thing. And then for case 2 is that if we found that this cuboid is floating at a certain draft, then we can know its weight, because we can calculate what's the volume inside that has been displaced, and that volume we can calculate, multiply by the rho of the water, and because it is a cuboid, the volume is just L times B times T times rho of the fresh water, the density of the fresh water. So that's the weight of the water being displaced. So this must equal to the weight of the object. So this is the example. So we found the bash 100 times 20 floating at draft of 5 meters. Automatically, we can know that the volume displaced is 100 times 20 times 5. Remember, we're using draft here, not depth. Yeah, depth is the total depth up to the deck. What you're talking here is this underwater volume. Underwater volume is up to draft. So we know the volume displacement to be 100 times 20 times 5, multiplied by 1.025 ton per meter cube, which is seawater density. and we got 10,250. So I need to mention about the density. Sometimes you're not given the density. Yeah. If not given, if they say seawater or salt water, use 1.025 ton per meter cube or 1,025 kilogram per meter cube. If fresh water, it is 1,000 ton per meter cube or one ton per meter cube or 1,000 kilogram per meter cube. If it is not given, if it is given, they use the given density. So same thing, exercise 2.3 is very similar to the previous example. And also exercise 2.4 is when you change water density. The same ship, the same box, it goes into river water, which has a lower density. So what happened to the draft? Or it goes into seawater, which is of higher density. And the density of seawater is not constant. It changes depending on the location and so on. So if the ship goes into a different density, then the draft will change. Why the draft will change? Because the volume displacement need to be more or less depending on the density, because the weight of the displaced water need to be the same, which is the same as the weight of the ship. Yeah. So if the ship same weight goes into a different water density, then it need to change the draft. Okay, 2.5 is just a cylinder, which is a bit different. So whatever it is, as long as we can calculate the volume of the underwater volume, yeah, the immersed volume, like this one is just the area times draft. That's the volume. So this we can calculate this area pi r squared times draft. Then we can get its volume multiplied by density. So we get the weight of water being displaced. And that weight is the same as the weight of the object. So that's example 2.6. Yeah. And as exercise 2.6. And exercise 2.7 is a bit more complicated because it is a rectangular. It's like a sheep, yeah. It's like a sheep, but it's a rectangular shape. Constant cross section from here to the end. So we need to calculate the volume of underwater, yeah, the immersed underwater volume only, which is that red dotted line is the draft. So we need to know what's the breadth here, so that we can calculate this area and multiply by the length, so we get the volume. So with that volume, we can get the weight of the water being displaced, and from there we can also know what's weight. So that's a question here. The question is asking, if it floats at a draft of 0.5, what is its weight? So we need to know how much is the volume displacement and multiply by the rho of 1.025 ton per meter cube. Then we can get the weight in ton. Yeah. But here also ask about water plane area coefficient, and so on. So which is quite easy actually. If you understand what water plane area, all these things, you should be able to find the values for this. Okay, so that's 2.7. And finally, is TPC. This is TPC. TPC is the weight required to increase or reduce. Oh, sorry, it's not trim. I draft. So please later you need to change that. To reduce draft by 1 centimeter is called ton per centimeter emission. That means that if the TPC of the ship is 100, that means you put 100 ton on the ship, the draft will change 1 centimeter. Remove 100 ton from the ship, it will reduce by, the draft will be reduced by 1 centimeter. So that's TPC. So sometimes you read in the data of the ship, they say TPC. TPC is 20, 10, maybe 150. So those are the value of TPC. So if we know the TPC of the ship, then we know how much draft is going to change when we remove or add weight. Yeah. So actually TPC is assuming that the water plane changes a little bit. So like this one. So this is the ship. There's a first water plane and that second water plane. The difference is 1 centimeter. So if you add a ship, you add weight to it, maybe initially it is floating at the lower water line here. Yeah. and so it is floating at this lower water line. This one, the bottom one. Oh, it's too thick, too thick. Okay, so it is floating at this lower water line. Yeah. So now if you add a weight that make it into 1 centimeter, so the water plane area times 1 centimeter, that is the water plane area times 1 centimeter, 1 centimeter, that is the volume that has increased. The volume, the immersed volume that has increased is the water plane area times 1 centimeter. And if you multiply, that is a volume. So that volume times the density, okay, is the uh, the the that the density is because density is in ton per meter cube or kilogram per meter cube. Then you need to divide by sorry, if you this one is in 1 centimeter, so 1 centimeter, so multiply by the density ton per meter cube, so you can get the value of the weight in ton or in kilogram depending on your density. It is divided by 100 here because this is 1 centimeter, 1 centimeter over 100, because to get this into meter. So area of the plane in meter times 1 over 100 in meter, which is 0.01, okay, and times densities ton per meter cube. So meter cube cancel out, yeah, and because this is meter squared times meter divided times ton per meter cube, so meter cube cancels, you're left with ton. So the additional weight that you need to add is ton. So that is the TPC, because the weight that need to be added to increase the by 1 centimeter, increase draft by 1 centimeter. So so this exercise here, this exercise is shipped with TPC 30, floats at draft of 6.5. What is the new mean draft if 150 tons are unloaded from the ship? So if you unload, that means the draft is reduced. So it's going to be less than this. How much is the reduction? If this 30 tons will reduce or increase 1 centimeter. If it is 150, it's 150, okay? So it is 150 divided by 30, and unit is centimeter, because 30 tons, 1 centimeter. Yeah, TPC means that of 30. So that means 30 ton reduce or increase by 1 centimeter. So if it is 150, then it is increased or reduced by 5 centimeter. So since it is you remove, so this need to be reduced. Okay, so that's the 8. So all this the solution to the exercises are all given in this Excel file. So you go to the first one just now. This is the question. Do calculations similar to example 2.1 to find the apparent weight of the cuboid in oil and mud. So you just change the density. 0.85, 1.3, and mercury of 13,000 kilogram per meter cube. Okay, so this is the original example 2.1 in the notes. Okay, so which was the calculation has been shown in the notes. Yeah, the blue one. I put 2 notes here. Density is sometimes expressed in kilogram per meter cube, sometimes in ton per meter cube. So make sure units are consistent. Like this is expressed in 1,000 kilogram per meter cube. So when you do the calculation, meter cube cancel, you get 1,000. You get kilogram, the unit. But if you use ton, then you ton per meter cube, ton per meter, in this case 1 ton per meter cube. So when you cancel out, it becomes the unit should be in ton. So be careful. Number 2, if fluid density, I've said just now, if fluid density is not given, always take seawater density as 1025 and fresh water as 1000. If it is given, then you use the given. If not, you can use this. So it is 1025 kilogram per meter cube or 1000 kilogram per meter cube. Or in ton will be 1.025, or this one 1 ton per meter cube. So how to solve that? It's given here. So the example 2.1 has been calculated. So this is the results. Yeah, you calculate the 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 fluid support or the buoyancy, right? And in this case, since it is fully immersed, then that means the total volume is based on D, L times B times D. Yeah, because the object is fully immersed. But when it is a floating object, remember, do not use D. In this case, we use D only because it is immersed. So the total displaced volume is L times B times D of the box. But for if it is later when it is floating, then L times B times T for a box. For a box, yeah. Okay, so again, we just calculate the support, which is this one, and 3 times minus the fluid support. So this is the results as required in the table. Yeah. So we have oil 0.85, density. This is fluid support. So this is the apparent weight. So that means that apparent weight in oil is more than apparent weight in fresh water because the density is less. But in muddy water, in muddy water, so it is thick. Yeah, the water is thick, so it is high density. So the fluid support is more because of the same volume times the fluid support, and the apparent weight is 0.4. And when you dip this same box inside mercury, the fluid support is 26 because of the high density of mercury. So because of that, the cuboid will have the negative sign. The support, the apparent weight is negative sign. Yeah, because it will have negative sign indicating that it is a force in the opposite direction to weight. Weight, all these are positive weight, that means down. 1.3, 1, 0.4, yeah? But for mercury, it is minus, showing that it is going up. So that means it is, this box inside mercury is just like a basketball that you push down in a pool of water. So you push, so you have a negative weight, which is positive buoyancy. Yeah. So when it is positive buoyancy, then this cuboid will move up and it will float in mercury. It will float when at a draft such that the value of the draft will create a volume that multiplied by the density of the mercury will be the same as the weight of the box, which is 3 tons. So you can calculate the draft in fact of this object if you want. So that's exercise 2.1. 2.2. 2.2 is we are looking at looking for draft. Yeah. Oh, why is it like this? Okay, so this is example 2.2 in the blue one, example 2.2 in the notes. So it's shown already the steps how to calculate this. So exercise 2.2 is similar to that. Do similar calculations as example 2.2 to find draft when the same cuboid block is floating in salt water and oil density 0.5. So basically, just ask you to exercise in changing the density of the do same calculation but just different density. So if you do that, it's the same thing, just similar calculation. But now note that the displacement is L times B times T times density. So note that it is T, draft, not depth, because the object is floating. Okay, the object is floating. Okay, this is floating, yeah, or in floating condition. So make sure that the density is in tons. Of course, it's not necessarily you must use tons, but as long as you're consistent, you can use one. If you use ton, then you use ton throughout. Yeah. If you can also use kilogram, where you can use this one as kilogram. So you change this one to kilogram. The this one. This one you can change into kilogram if you use the density as in kilogram. So volume displacement is 1.45 times 0.5 times t. T we don't know yet. Okay, but we know the weight. So by this formula, we can get the T by dividing the weight by the volume displacement times density. So not the volume displacement, the length times B times density, because T is here. So we make this table. Of course, you don't have to make a table, but I made a table because we have different density. So the freshwater one has been done in the example 2.2. Okay, this has been done. So just use salt water 1.025 and oil 0.85, and we get this T to be changing. So we see here the object is same weight 0.1454, but when it go into fresh water, it is 0.212. It go into salt water is less draft. It go into oil is more draft. Why? Because in salt water the support is more because of the density, so you need less volume. You need less volume also, you can get same weight. Yeah, that's why the draft is less in salt water. Whereas in oil, you need more volume. That's why the draft is more, because the density is small. So that's the concept that we want to see here. Okay, we go to exercise 2.3. Okay. So exercise 2.3, we want to find the weight if we know the draft. So this is much more simpler. Yeah. So it's basically by knowing the draft, we know if it is a block of wood, it's a cuboid, then it's just length times B times not D times T, you get the volume displacement. So that volume displacement times rho, the density, okay, LBT times density, you get the weight displacement. And with that weight displacement, that is the same as the weight of the wooden block. So very easy to find the weight of something if you know the volume. So this is the thing that you need to use in your floating structure competition. Yeah. So you can expect what is the draft of your floating structure, the floating structure that you design, by calculating the weight, the weight of water going to be displaced. So they're basically calculating the displaced volume displacement that you need, that the object push aside, yeah, as it goes into the water, and that should be the same as the weight that you want to add. So if you say you want to add 1 kilo together with all that weight, the 1 kilo is your dead weight, yeah. So you need to know what is the weight of your original light ship, which is the empty structure only. So say for example the weight of your empty structure is 500 gram, half a kilo, and you want to add 1 kilo, so the total weight is 1.5 kilo. Light sheet plus dead weight, 1.5 kilogram. So if it is 1.5 kilogram, you need to provide the volume displacement of, in fresh water will be, you need to provide the 1.5 kilogram of water, displaced volume. So that's how you do it. Okay, so this is easy enough. Example 2.4. It's again the same one. Basically, you change this one. You know the example before this, yeah. This one, just different seawater density. So you can do the same thing like this. In this seawater density, what is the weight in tons? In river water, so in fact this one is, this should be colored blue, yeah. This should be colored blue because this is this example 2.3. So the weight is, you can get 10,250. So if it is the same draft, but You see, this is the same shape, but it goes into the water, same draft. That means the weight has been reduced if the draft is the same. So the weight is 10,000. Okay. And if this is another seawater, okay, seawater, which is 1.1 tons, then 11,000 because of the density is different. This is seawater, but this density is different. So when it's higher density, if it is floating in the same draft, it is 11,000. So note that a barge floating at the same draft in different location, different density have different weight. Yeah, the low density water will mean less weight. Okay, 2.5. 2.5 is the cylinder. So as we said just now, what we do is we can calculate this volume. Okay, how do you calculate the volume? Just area of the water plane multiplied by h, or multiplied by t. So we get the volume, and we know if we know the volume, yeah, then we can know its draft. So in this case, we do not know the draft, yeah. Uh, so in this case, we do not know the draft. There's something hidden there. So this should be the way. So it's the same thing. If it is cylinder or anything, any object, if it's floating, find the weight. That weight must be the same as the weight displacement of the water. So in this case, you see this formula. So this formula pi times r squared, because the diameter is 1 meter, so r is 0.5. Pi r squared times t, is the area times draft. Okay, that's the volume. So multiply by density, you get the same as the weight of the cylinder. So from there, you can find what is T. You know the weight. Yeah, in this case, we know the weight. We are given the weight in the exercise. Okay, 5 ton. So we can get the draft. Oh yes, sorry, the mistake here. This one should be. Oh, this is the same one. Okay. Right. Okay. I copy, cut and paste. But the thing is, seawater or and oil. So we see that the same object, same weight. If it is in seawater, the draft is 6.21. Okay. Well, if it is in oil, the draft is 7.32. Same weight, same cylinder, because of the low density of oil. So you put this inside oil, then it sink deeper because you need more displaced oil to support the same weight. Yeah. So note that the cylinder is floating differently at different weights. So in this case, sorry, this one should be again different draft. Oh dear, okay, some mistake, eh? All right, that's 2.5, 2.6. Cylindrical tank. So this one is just we need to know the draft. And we find the weight cargo to be added. This one, weight to be added, to the one to be added. This part on the so that one is still the same, yeah. The calculation is still the same, and then to find the weight to be added, we know there are two drafts. One draft initially of okay, the one that we calculate, find it. Here we know the weight of 200 kilogram. Okay, so find the predator draft. That's exactly the same like the previous calculation. So we calculate the draft to be 0.79. And then Okay, so this is the draft that you calculate. And then to find the weight to be added, add draft. So now it's floating at 0.79. Now, if you say now you want to bring the ship or the cylinder to 0.85, the draft. So there are two drafts. So you find the new displacement or new weight of the cylinder by finding the new displacement at 0.85 meter. So this is the new weight at 0.85. Yeah. So because of that, you know that the added weight is 214 kilogram minus 200 kilogram, the initial one. So you get that to be, you can do this calculation in kilogram by using the density in kilogram, yeah. But here you get the difference will be 0.14, which is 14 kilogram. So that means if you add 14 kilogram, then you get that difference. But the thing will sink deeper into 0.85. From 0.79 it goes to 0.85. Okay, 2.7. So this is a bit more complicated because it needs you to understand what's happening here. So we have this barge. It is floating like this. Yeah. And this is a draft of 0.5 meter. And that breadth up there is 2 meters. And this is 0.7 meter, the depth. Okay. So if it is floating like that, so this is, you see from this direction, then this is how it look like. So this is the one that is submerged underwater. The yellow one is the freeboard. So this is freeboard. So this is depth 0.7. This is draft 0.5. Okay. So the difference here is a freeboard. So we don't care about the freeboard. What we want to know is the breadth at this part because we want to calculate this area. If we know this area, if we know this area, okay, this orange part, then we can, this is this area here. Okay. So this is the orange part. So that is basically the water plane for this particular draft. Yeah, so the one like that. So this is the underwater volume. So the volume is just this area because that's the same area. So area times length. So we want to find this area. To find this area, we need to know B. So you need to know B, right? So we need to know B here. Yeah? We need to find B. So B is just, this is a triangle. So B is just 0.5. Basically, B over 0.5 is the same as 2 over 0.7 because this is a triangle. Yeah? So B over 0.5. If you measure from here, 0.5. So B over 0.5 is the same as 2 over 0.7. So because of that, you can find B to be 1.43. So here is 1.43. Okay. So once you know that, then you can find the volume displacement because you find this area, which is half times 0.5 times B. That is volume displacement. And the weight is times density 3660.71. So we can get 3.661. Right? So the question asks you for the weight. So the same thing, as long as you can find the volume displacement or volume displaced or the displaced water, weight of displaced water, you know that is the weight of the floating object. That's all. Whether it is a bottle, whether it is a ship, whether it is a triangle, whether it is a box, whether it is a cylinder, whether it is your floating structure. So you want to find the draft, you can calculate by putting the weight similar as the volume displacement. If you want to know the weight, but you know the draft, you can calculate the volume displacement multiplied by the row. So that's basically the idea. That idea is the one that is important. This whole concept for this lecture or this particular notes, yeah, it's about that. And then the last part here, find also is water plane area coefficient, block coefficient, prismatic coefficient, and so on. This is only to test you about your understanding of this. We know what is water plane area. It's just the area of the water plane. So in this case, it is just a straight, it's a box, like I drew just now. Yeah, I drag it. It is just a box. Here, straight here, and here, and here. So this is the thing. So you know this one is 1.43 or something just now. Multiply by the length, 10 meter. So that is the water plane area. This one. Yeah. So if you know that's the water plane area, then you can calculate the water plane area coefficient. Water plane area coefficient is the box, it is the area divided by the box surrounding it. Okay, so in this case should be 1 because the box is so L times B. Yeah, B of that particular water plane area. So the block coefficient, you know the volume, you have to calculate it down here. The volume displacement. This one, the volume displacement. So you divide by the box surrounding it. The box is L times B times T. The B is not the 2 meters, it is 1.43 meters, which is this one. So the box surrounding it, oh dear. Okay, okay. So this is the volume underneath, yeah. So the box surrounding is L times B, 1.43 times T, which is 0.5. So that's CB. And then prismatic coefficient. Prismatic coefficient is volume divided by area at midship section, which is in this case is same as this area, and multiply by L. That's prismatic coefficient. And LCF, since it is the water plane, it's just a box. Yeah, it's a box, a rectangular box. So LCF at midship, LCB at midship. KB you need to calculate here. Where is it? It will be 2/3 from the bottom. So it just, that's KB at that point, yeah? So 2/3. So example, that's 2.7. And finally, 2.8, I have explained just now when we were looking at the notes. Because if a ship has TPC of 30, okay, it means that 30 ton will change draft 30 tons, TPC 30 ton will change draft by 1 centimeter. If 150 tons is unloaded, the ship will rise. So rise means the draft will be reduced. So the parallel rise, we call it, or reduction in draft, how much is reduction? So reduction is weight removed divided by TPC. Weight removed divided by TPC. Because 30 ton change 1 centimeter. If 150 divided by 30. So you get 5, but you need remember, it is centimeter. Because 30 ton change 1 centimeter. If it's 150, change 5 centimeter. So you change that into meter, then you can get new draft is original draft minus reduction draft, 6.45 meter. So that's all for the 8 exercises that we do. It's almost exactly 1 hour or 50 minutes. We've gone through from the notes and so on. So I open if there is any question or anything you want to raise before we end. Let's see how many of you are here. Participants. Okay, 10. That's good. Right. Anything you want to ask or raise, you can ask now or you can ask. Okay. Any you ask through chat or you can also switch on your microphone. All right. I read the chat that's relevant. Maybe. Just the question is our test will cover till where? Our test will cover up to test 1 will cover up to this class only. Up to here, test 1. So Uh, uh, so only week 7. Well, week 7 is actually a revision of all the previous weeks, yeah, and then up to week 9. So that's what we do. So we will do the test not this week, not next week. It's the week after. So just so that you may know your results, just in case you feel that it's very difficult to this subject is very difficult, you're not going to make it and so on, you can still have time to withdraw. You can drop the subject before 15th of May. Okay. So if you feel that it is very difficult and because of we learn online and so on. But normally, if it is normal learning, normally if you do the things and so on, normally you don't fail. But just in case you say you want to score properly and so on, you want to wait for better one and so on. Okay. Will the formula be given? No. During test, we are not going to give you formula. You have to remember. Many of the formula here are very basic that you have to remember because this is what you're going to use and throughout your life. So you must very, very basic thing. It's not the formula that's important. It is the understanding. Okay. How do you calculate? It's not that it must be always L times B times D. Yeah. So it depends on the shape of the object. If the shape is a ship, you have to calculate the volume of the ship. If the shape is a bottle, like in uh, your floating competition, floating structure, then you must calculate that bottle volume. Yeah. If it is a cylinder, it's a cylinder. If it is a prism, then it is prism. Okay. So we'll have our test within next 2 weeks. Yes. Any other questions? No? Okay. So in that case, we end here. I have another meeting at 11 o'clock. So if anything, you just you can PM me if you feel shy, you asking in the group, yeah. You can PM me or you can even call me. I can call you back if you feel that you need help, yeah. For example, you have one that's one part of this exercise that you really do not understand. You can call me and I'll call you back and I'll explain to you. All right. Okay. So we are here to help you actually because everybody is having problem, of course. Well, not everybody, yeah. Many people are having problem in terms of connection, in terms of difficulties in studying and so on. Yes, we can understand. That's why we try our best. So that's why the faculty has extended the 4 weeks of our semester, so that we have more time to deal and repeat things and so on, do things. So that's what we're trying to do. Uh, we will allow that. In fact, for your floating structure competition as well, I've discussed with Dr. Xiao. We are going to relax a little bit more in terms of your deadlines. It's not going to be as he has announced. Maybe we'll have sometime in June as our the ending for that project, the group project, so that you have more time to things. In fact, for your group project, you need to understand this. Yeah, part of your report, you must do calculation of hydrostatic flotation and so on, and also stability, which is the next module. Next module is on stability, so you need to understand the next module. Okay, so that's all for today. Thank you very much for attending. We hope that you have understood what need to be understood. Okay. Okay. Thank you. Assalamualaikum warahmatullahi wabarakatuh, and have a good day.